This lesson is going to talk about the summary of triangle centers. There's a couple of vocabulary words you need to know, which is point of concurrency. This is the intersecting point of three or more lines. So a point is created when three or more lines intersect. We can also talk about concurrent lines, which is where three or more lines that intersect at the same point. So those are kind of the same thing, but talked about in a different way. So there are four types of concurrency points: the centroid, the incenter, the circumcenter, and the orthocenter. So we're going to break these down, and the first one we're going to talk about is the centroid. So the centroid, the reason we use this, and it's kind of a balance point or a center of gravity. If we were to take a triangle and find that center of gravity on our finger, on a a stick, we could balance it through where the centroid point would actually be. So this is an average position of all 3 points in a triangle. And they're created by intersections of the medians. And medians go through the midpoint of the sides, which creates two congruent sides, and then through the vertex, the opposite vertex. So they do have a special ratio that is created when the centroid divides the medians into pieces, and that is a 2-to-1 ratio. So for example, I've already drew here our centroid, and I have marked it in yellow. So let's look at here. So let's say if I was talking about from this segment to the middle point, which is our centroid, versus the same line but on the other side of the centroid, notice that they're different sizes. This is where our 2-to-1 ratio comes in. So if this was 2, this would be half of that, which would be 1. And the same thing is true for all of the segments going from the vertex to the midpoints on either side. And so we'll see that in our examples. When we do centroids, they're always found, no matter what type of triangle you have, inside of the triangle. So we're going to talk about the acute one first. I went ahead and my midpoints are here on each side. So our little midpoints on each side. So that we found by measuring. I measured with a little ruler first to break them up. And then it goes from my vertex through to my midpoint. And I've created 2 congruent segments here on each side. Notice our ratio 2-to-1, just marked it for us. 2 is always towards the top part near your vertex, and the 1 part near your midpoint that you are going to. So notice it's in the center. If we do the same thing with a right triangle, and this is right because of our right box, so make sure that's added there. I'm giving that to you. And then notice how we create our midpoints, created some congruent sides, and the same thing with obtuse. So they're always in the middle, and that is helpful to know that they're going to be in the middle. It's very helpful to know our 2-to-1 ratio so that we can help find other pieces. So you're going to be given some problems on the next part to use this knowledge and see if you can find some missing pieces. So here we're given that K is a centroid, so in the middle, already labeled, and that AK, so from A to the centroid K, is 5, and you want to find KD. Well, if we look from the vertex down to the midpoint, we know that the top part on top of the centroid, where K is the 2 part, the 2-to-1 ratio. So if this is 5, then this is half of 5. So we would have this as 2.5. Now also notice that we have some pieces not marked. Being told that they're the centroid and these pieces are going through, we automatically know if this side DB is 5, then CD segment is also 5 because it creates 2 congruent pieces going through the midpoint. Same thing with A here. Maybe we call this E. A to E is 3. That means E to B is also 3. And then from C A, the whole section here will be split into a midpoint. We could think about this if we call this F. A to F is 8, so C to F is also 8. Okay. So try this one. You're given G is the centroid. I'll mark it here. And AF is equal to 12. And we want to find all the missing pieces. So pause for a moment and see if you can find them. So if we look what we were given, we can easily find the outsides because we know that G is the centroid. we know that it creates congruent segments through the midpoints on the sides of the triangle. So that's easy to do. We were given 3 for CG, and it's the bigger part coming from the vertex of the centroid. So we know that the other part of its segment, GE, would be half of that, so 1.5. Same with the B all the way to D. We were given GD is 2, and it's a smaller part of that ratio, so we can double it and find that BG is 4. Now with the pieces we were given A to F, we know that the top part is 2x, or 2 times, because the ratio 2 to 1, it's 2 times whatever x is, and x we don't know, so 2x plus x is 12. We solved for that. We found that our smallest part, this would be 4, and then we double it, and this would be 8. Our next type we're going to discuss is incenters. So the specific feature for these is their equal distance of all 3 sides of a triangle. You should know what equidistance means after your vocabulary earlier. And these are formed by intersection of angle bisectors. Another vocabulary word. So an angle bisector splits an angle perfectly in half. And the location of these also, just like the previous one, are always inside. This actually maximizes the area of a circle within the triangle, and you'll see those on the examples. So angle bisector is a line that actually cuts the angle right in half, and so we're going to end up having some pieces that are angles that are congruent. And it just goes straight through. It doesn't really matter if it goes to the midpoint. It could. On some of them it will, but it will cut these angles right in half. So it makes 2 congruent angles. So we'll do that for each piece. So let's look at another one. Right through angle bisector. Of course, it's a straight line, so this will make these congruent. We'll do those with 2 arcs. And then the last piece through the vertex or angle bisector. It's bisecting the angle into 2. Bisect means it's going to make it, and this makes it equal distance between all 3 sides. So we end up here having our incenter. Now, our incenter, we can kind of see, it helps us know that the angles are the same. Notice inside of an acute, it's inside, okay? And if we do the same thing with the other 2, you'll see that they're also inside. So take a moment, draw yours out, and see if you get what you should. So you should have gotten, when you drew, all 3 of the incenters, no matter what type of triangle, they're inside. That's important to know. So when your takeaway from this is that this feature, this incenter, is the equidistant. So from any point, from here to any point, here, 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 it's going to be equidistance away from the sides of the triangle. It's not always easy to see when we don't have a scale to measure, but it is. So when we think about what has happened and why we do this, we're actually doing this to maximize the area of a circle within the triangle. And right now you don't see a circle, but we can actually inscribe a circle inside the triangle. It's touching all parts. And this creates an area of that circle that's the largest. So it kind of helps us know the radius, and by knowing kind of where the incenter is and the equidistance from the sides, we can find out a lot about other information. Talk about circumcenter. That is our third type. And these are equidistance from each of the 3 vertices of a triangle. And they're formed by perpendicular bisectors. So I went ahead and marked my midpoints. So if I look at my midpoint here, and I'm going to do a 90 degrees, it's a perfect 90 degrees. Notice that it barely, this one cuts almost exactly there. And of course I measured these. And so there's one. And we'll do one in a different color. So we're doing a 90-degree angle through, and we have there, and we're doing a 90-degree here, different color, and pretty close there. All right, so notice for our acute, it is inside. This is our circumcenter, it is inside. This does bisect because we found the median, so this will be congruent to this. These 2 pieces would be congruent, and these 2 pieces would be congruent, and it's at 90 degrees, our perpendicular bisectors. So it's not necessarily always going to be right in the center. This one looks beautiful. This is the circumcenter. It's great to remember that, but we're trying to see what it would look like in other ones. So let's look at our right one. So if we think about a middle, and I haven't measured this one yet, so this one is about 5 centimeters, so we're going to roughly say angle bisector would be here. So if I go up from perpendicular straight up, that's 90 degrees. I have a 90 degree. I've created two congruent segments. Notice I didn't go through a vertex at all. If I did a 90 degree here already, because I already measured, and I go through, so 90 degree, and then I'll do another color here, and 90 degrees, and here. Then here is my circumcenter. And notice it is not inside, it is actually on the side. It is on the side here for my right triangles. Now for our obtuse ones, we have to follow the same procedure. Try to avoid trying to make something out of something that's not. So a lot of times people will try to tilt their perpendicular bisector, so don't do that. So we're going from the midpoint here that I've already marked, and we're making a 90 degree angle. So if we think about extending a 90 degree angle, or a line that does perpendicular bisector, makes 90 degrees, we've created two congruent pieces. Okay, we can do the same thing for the next side. So I've marked my midpoint here, and we want to go directly through this line, and I'm going to extend it both directions, so we can do a 90 degrees right through here. Okay, and if we extend it this way as well, you can see it's not going through a vertex, but it made a 90 degree segment as well. And then we'll take our last one, and again we'll do a 90 degrees perfectly up and down. And that one, pretty close there. And we have our point right there in the middle. So this is created two pieces. The other side created from here to here as congruent by the angle bisector. So for a obtuse triangle, when we do a circumcenter, we have it on the outside. And this is the equidistance from each of the vertices. So what I mean by equidistance, if we look here and we're going from this vertex and we're going to our point, because it's equidistance from here to here, and from here to here, and here to here would all be the same distance. So this is helpful when maybe we're trying to build a new building or a gym or a store, and we are between some towns and we want everyone to have equal access to it. That would be something that would be thought of and we can use in real world examples. Orthocenter. Orthocenters don't have any specific features, but they are formed by intersections of altitudes through the vertex, and we're just not worrying about where we're hitting, we just know we're creating a right angle. And we'll do another one through the vertex and creating a right angle. And lastly, through the last vertex and creating a right angle. Now, we don't know that we went through the midpoint, so we can't say we have congruent segments on the sides, but we do know that this here would be our orthocenter. So let's look and see what our orthocenter would look like for a right triangle. So remember, we're going through our vertex. That doesn't mean we're angle bisecting. It just means we're going from our vertex to create a right angle. So I'm going to start from the right angle vertex, and I'm going to go from it. So I'm starting it, and I'm just going at a perpendicular fashion to make a right angle. And I'm going to extend it out just a little bit, just in case I need to for later. We don't know. We won't necessarily need it. I'm going to go and do that. So make sure you understand the purpose of what you're doing, and this will make a little bit more sense. So we're trying to find the shortest distance from an angle to the opposite side. So if I'm thinking about where my angle is, where I just started, and to the opposite side, I'm trying to find that distance. So when I'm going from, let's say, this top vertex, so if I start here at this vertex, I'm trying to go to the opposite side. The opposite side is right here, okay? So I'm doing a 90 degrees. I'm not doing an angle. That's not 90 degrees. I'm going 90 degrees. So I'm going down 90 degrees. It also makes a 90 degrees right here at this box. Okay, so that one's done. And then if I do the last one, I'm going from here to the opposite side. The opposite side from this would be over here. And I'm not going at an angle. I'm not bisecting the angle. I'm just going from the vertex to the opposite side at a 90 degrees. So I could think about this one as well, going 90 degrees this straight way. And this is also 90 degrees. So where they all would intersect would be right here on the side. Now the obtuse one can be a little challenging when you first try to look at it. So one of the things that's helpful is notice we're going from the vertex to the opposite side. So when we think about this vertex here, if we start at this vertex here and we're doing a 90-degree angle from the vertex to the opposite side, and we're making a 90-degree angle. And we can think about this could extend, if we needed to, this way, and it also can extend this way. So I'm going to go ahead and extend it. The other ones you think about, if you're going from here to the opposite side, our common thought would be to go right through and to hit it. But that wouldn't be at a 90-degree angle. So it's easier to kind of think about, we're talking about this side right here. So let's extend that side out so that we can do a 90-degree angle. So we'll go from here, from our vertex, down. And I'm extending a little bit longer because we want a point that intersects. And this is now hitting that angle at a 90-degree angle. Okay, so we've done those two. Now we have to do this one as well, this last vertices. And so we have a vertices here, and we want to go to this opposite side here, and opposite would be here from it, and we can't go through the middle. So let's extend that one down as well. So we're going to extend this one. That same side will be extended, and then from there, it's easy to see that we could draw a 90-degree angle. So we're going to go here. Make sure that's 90, and then we'll extend it on as well, making sure we're keeping 90. Yes, we are. That's a 90 angle. So now where they intersect is our orthos. So it is on the outside of an obtuse, and it's extending those sides, knowing that we're going to the opposite side, helps a little bit with those, but it is always on the outside.